everyone. Oh, blurry. Okay, in this example, I want to try out several of the things that we've talked about. So I want to find critical values, and then I want to try both the first and second derivative tests just to kind of compare and contrast. And then I also want to make sure we talk through the algebra of finding the inflection points. We've said what an inflection point is, but we've never gone looking, starting from an equation, to see if we could find one. Okay, so if you want to find the critical values of your function, you need a derivative, right? Critical values happen when the derivative is 0 or undefined. So in this case, my function x squared e to the negative x is a product. So I'm going to have e to the negative x times the derivative of x squared, 2x. And then I'm going to have x squared times the derivative of e to the negative x, which is a little chain rule there. E to the negative x is its own derivative, but chain rule says it has to get multiplied by a -1. E to the stuff is its own derivative. Okay, and then simplification, this is exactly where factoring becomes really handy. So I'm going to factor out an e to the negative x, and I'm also going to factor out an x. So x e to the negative x, and I'm left with a 2 and a minus x. Okay, so if I want to know when h prime equals 0, I have this thing factored, so I should just be able to look at it. So we kind of have like 3 factors, right? This is multiplication and this is multiplication. So the first factor is 0 just by letting x be 0, and that would make the whole thing 0. E to the negative x is never 0. Remember those exponentials. It doesn't matter what power you raise that to. It's not going to completely get rid of the number there, so that's not going to happen. But this one does. If x equals 2, that one is 0. And then we also want to know when h prime does not exist. And in this case, that's not a problem. It never happens. H prime. Okay, sorry, making weird noises. Looking at this, I guess, there's never a problem with an x or a 2 minus x, and exponential functions as well don't have any domain problems. So that's a never, which means my critical values are just x equals 0 and x equals 2. Okay, so 2 critical values. And now we're going to move on and try our first and second derivatives. So first derivatives, that involves checking, and again, think really carefully about this. That involves checking nearby on either side of each critical value to see what's going on with slopes. So we're going to say, let's make a quick sign chart. I'm interested in what's happening at x equals 0 and x equals 2. And let's see, at x equals 0, so this makes f prime 0, so these are both flat spots. So I'm going to try plugging in a -1. If I plug in a -1, and I'm going to use the factored form, I just like that. You can use whatever you want, -1. I get a -1 multiplied by e to the 1, which is positive, multiplied by 2 minus -1, which is 3, which is positive. So that ends up being negative. Okay, in the middle, I'm going to check a +1. At +1, I get 1, which is positive, multiplied by e to the -1, which is still positive. Negative power makes it 1 over e, which is around 1/3. And then 2 minus 1 is 1, so here is positive. And then if we want to try 3, at x equals 3, x is positive, e to the -3, still positive. Not both of these, this is always positive. And then 2 minus 3 is negative, so it goes minus plus minus. Okay, so what we're seeing, so this is f prime. What this is telling us about f is that here's a flat spot, and the function increases and then decreases, so that is a maximum. At 2, there's hold on, somebody's backwards. The function decreases and then increases, so that's a minimum. Try again. At 2, the function increases and then decreases, so that's a maximum. So we have a min at x equals 0 and a max at x equals 2. Okay, so that's how the first derivative test looks for this. For either one, you're going to have to find the critical values. So this is the work specific to the first derivative. If we want to use a second derivative test, we first need to find the second derivative. So this is usually the deciding factor for me. Be prepared on the test for me to say specifically to use first or second derivatives, but on your homework I didn't do that because I want you to think about when is it a good idea to use the second derivative test versus the first derivative test. And I would say the second derivative test is a great idea if you have things like polynomials that get simpler every time you take a derivative. Here, things get a little bit messier. So let me think about this. I actually don't think I like this form of the derivative for taking a second derivative because I have double product rules. So I'm going to distribute it back in and say I have 2x e to the negative x minus x squared e to the negative x. I still have to do product rules twice, but it's not one inside of the other. So it's up to you what you think is better. Okay, so for this first one, ignoring the second term, 2x e to the x. I want the second e to the negative x, not x, times the derivative of the first. The derivative of 2x is 2. And then I want the first, 2x, multiplied by the derivative of e to the negative x, which is e to the negative x multiplied by negative 1. So I'm just going to change that sign right now so I don't lose track of anything. And then I have a negative x squared multiplied by an e to the negative x. So I'm going to do that e to the negative x multiplied by the derivative of negative x squared. So negative 2x e to the negative x. And then I'm going to take that negative x squared and multiply it by the derivative of e to the negative x, which is e to the negative x multiplied by a negative 1. That'll make that a positive. And I can simplify a tiny bit. Right here, the negative 2x e to the negative x minus 2x e to the negative x, those are like terms. So I can say that that is a 2e to the negative x minus 4x e to the negative x's plus x squared e to the negative x. Okay, so the second derivative test. This requires me to take my second derivative and plug in each of my critical values. So again, the first derivative test, you don't plug in your critical values. If you plug a critical value into the derivative, you should get 0 or undefined. That's how we got them. We already know that. It's the second derivative that you can actually get new information from. We don't yet know about the concavity at those points. So we're going to try h double prime of 0, which is 2e to the 0, which is 1. 4 times 0, e to the 0, that's 0. 0 squared e to the 0, that's 0. So this is just 2. The key thing here is just positive or negative. So because the second derivative is positive, that means at our flat spot, the function is bending up. So as opposed to using decreasing, increasing, we use bending up to say that that's a min at x equals 0. For h double prime of 2, we're going to get 2e to the negative 2 minus 4 times 2, 8 e to the negative 2 plus 4 e to the negative 2, which combines 6 minus, so it's negative 2 e to the negative 2. 6 e to the negative 2 minus 8 e to the negative 2. Which, again, e to the negative 2 is positive, so this whole thing ends up being negative, which means at our flat spot, the function is concave down, which tells me that there is a max at x equals 2. Okay, so in this case, because the derivative was kind of messy, I think that the second derivative test was a little bit harder. But in problems where the second derivative is really easy to take, the second derivative test is probably easier. So make sure you practice both. I will very likely specify one on the test or both, or maybe leave it up to you. Just be prepared to show me either one, but on your homework, you can pick and choose and try and be smart about it. Okay, last part of this problem is to find all the inflection points and then try and put this info together to sketch the function. So to find an inflection points happen when the bend of the original function changes, which happens at the maxes and mins of the derivative, not of the function, of the derivative, which happen when the second derivative is 0. So we want to take this second derivative the 2e to the negative x minus 4x e to the negative x plus x squared e to the negative x, and set it equal to 0. And I can factor out an e to the negative x. I'm left with a 2 minus 4x plus x squared equals 0. And that does not look very promising on the factoring, but I can use a quadratic formula. So we have two factors. E to the x is never equal to 0. I ignore that. But 2 minus 4x plus x squared could be. So my quadratic formula says I want to take the opposite of b, which is a positive 4, plus or minus the square root of b squared, which is 16, minus 4 times a, which is 1, times c, which is 2. So that ends up being minus 4 times 2 minus 8. I guess I don't need to write that. All over 2a. A was 1. Okay, so x is 4 plus or minus root 8 over 2. It's fine if you leave it like this. I don't really care, but I will point out that if you extract roots, this is 4 times 2, square root of 4 times 2. It turns into 4 plus or minus 2 root 2 over 2, which turns into 2 plus or minus root 2. No more fraction. So that is kind of nice. And we want to hopefully get to claim that these are inflection points. The second derivative is 0 at 2 plus or minus root 2. But you can't just jump straight to it, just like you can't jump straight to saying the critical values are the maxes and mins. These are the potential inflection points. So setting the second derivative equal to 0 and solving gives you potential inflection points. What you have to do to confirm that they're inflection points is to, sorry, I'm not very literate today. I'm not very good at speaking. Okay, what you need to do to make sure that they really are inflection points is to make sure that the second derivative really does change sign. So a sign chart is the easiest way to do this. Root 2 is kind of in the ballpark of 1.4. So from 2, we're going to go plus 1.4, which will put us at about 3.4. So this is the 2 plus root 2 over here. And then if we want to go minus root 2, this is 2 minus root 2 over here. So this is around 3.4, and this is around 0.6, which means I could plug in 1. And I could plug in 3 to figure out what's happening there. Okay, so hold on, 0. And this is a second derivative. This is f double prime. And I could plug in 0. And then on this side, I could plug in 4. Okay, so I'm plugging them into the second derivative. If I plug in 0, ooh, I've actually already done some of this. If I plug in 0, I got 2. So this was positive. H double prime equals 2. When I plugged in 2, which is nicely in the middle. Oh, I don't even need to plug in 2 here. I was saying I was going to test 1 and 3, but that's actually a little silly. I can just plug in 2 in the middle, which I've already done. And I found that the second derivative was negative at x equals 2. So actually the only one I really need to do any work for is the 4. So h double prime of 4. Where's my second derivative? So that's, well, I didn't leave myself very good room. 2e to the negative 4 minus 16e to the negative 4 plus 16e to the negative 4. So the 16e to the negative 4's go away, and that ends up being positive. Okay, so at the 2 potential inflection points, I do find that my function was concave up and then concave down for the first one, and concave down and then concave up for the second one. So they really are both inflection points. You have to check, though, it absolutely is possible for your function to be concave up and then kind of flatten out so it looks linear for an instant and then go back to concave up. So always double check. That's really important, and I'll look for that on tests. Thanks for watching.